So the next theory to explain the electrical conductivity and many other properties of the conducting materials, Sommerfeld introduced quantum free electron theory with major assumptions. So there in quantum free electron theory, the major assumptions were the energy values of the conduction electrons were quantized. Important assumption of quantum free electron theory. Here the energy of the electrons or the particles involved possess definite energies. They are quantized. And there is another important assumption is the distribution of electrons into various energy levels follow Fermi Dirac statistics and as well which that follows the Pauli's exclusion principle. Then we have understood to some extent the Fermi level and Fermi energy. The Fermi energy, that is with respect to Fermi energy, it is the highest occupied energy state at 0k called the Fermi level. I mean Fermi energy, and the corresponding level is called the Fermi level. And you know that at T is equal to 0k, EF, that is the Fermi energy, is the highest occupied level. So the levels below EF are filled and levels above EF are unfilled. Then we come to the, so this Fermi factor is represents the probability of occupation of an energy state. So the electron has to occupy some energy level. So how much it is occupying, what is the probability of occupation in this particular energy level is given by the Fermi factor at any given thermal equilibrium. So we can define the Fermi factor as it is the likelihood or the probability of any given energy state in the material at thermal equilibrium is called the Fermi factor. This is also called the Fermi function. And this Fermi function f of E is given by 1 by 1 plus exponent of E minus EF by kT. So here in this expression EF is the Fermi energy, E is the energy at any temperature T, the capital T, K is the Boltzmann constant. And this f of E is already stated, it is the probable value. So from mathematics you know that the probability is varying from 0 to 1. Probability varies from 0 to 1. The value of probability is 0. It means that particular event does not exist. Here in this particular case with respect to the electron, if the probability f of E is 0, it means that that particular state is unfilled or it is empty. And if the probability happens to be, if it happens to be 1, then that particular state has been occupied or it is called the filled state. Okay. So now in practical, you cannot expect all the time it is 0 or it is exactly equal to 1. So the probability is anywhere between 0 to 1. So now that is the probability. Now what we study here, the variation of the f of E versus the energy. Here look at the plot at the right side. We try to understand the dependence of Fermi factor with respect to the energy at different temperature conditions. What are the probable temperature conditions? Either temperature 0 or greater than 0. You cannot have temperature less than, 0. Here 0 means 0 Kelvin. You can't have a temperature less than 0 Kelvin. So only two probabilities. The temperature either is 0 Kelvin or, and we look at the temperature more than 0 Kelvin. Here therefore, and we'll understand the probability of occupation at 0 Kelvin for all those energy values, for all those energy levels less than Fermi energy. In the last class you have observed, I have seen that EF is the highest occupied level, and if you try to find the probability of occupation of any energy level less than EF, and in the other case we are trying to, in another case we are trying to find the probability of occupation for the levels that is above EF at the temperature T equal to 0 Kelvin, and the other probability is that temperature is other than 0. What is the probability of occupation at any temperature T greater than 0 Kelvin? So now we'll study the one by one, the case wise. So this is the first case where they were trying to understand, they were trying to find the probable values of occupation for the energy levels less than that of EF. That is, we are trying to see theoretically, we are trying to observe the theoretical values for the probabilities of any occupied state that is below the Fermi energy at t equal to 0k. Okay, now if you assume, see, already we have the expression for probability f of E occupation, that is Fermi factor, that is equal to 1 by exponent of E minus EF divided by KT plus 1. So look at here, our situation is temperature is 0 Kelvin, and we are looking at the energy levels with respect to the electrons, all are below EF. We are looking at the levels below the Fermi energy. Look at the bracket, within the bracket that is with respect to exponent within the bracket E minus EF. Since E is less than EF, E energy level you under consideration, it is below EF. Therefore, it becomes the bracket becomes negative. So negative value divided by some k into T. Since temperature T is 0, so some negative value divided by a 0 value gives you the infinity, minus infinity. Therefore, the f of E is equal to 1 by e to the power minus infinity plus 1. And again you can write e minus infinity as 1 by infinity, and if you substitute for infinity it is 1 by 0, therefore 1 divided by 1 by 0, so 0 goes to the numerator, therefore it is the entire e minus e to the power minus infinity becomes 0. So now you look at the expression, so in the denominator it's only 1, the value is equal to 1 because other e to the minus infinity is 0, therefore f of e becomes 1. Now that is when temperature is 0 Kelvin and you are looking at those energy levels below EF, that is below Fermi energy, and you will see that probability is 1. It means the probability of occupation 1 means it's 100%. F of E1 implies is equal to 1 implies that the occupation is 100% at T equal to 0 Kelvin. Theoretically speaking, it is see, in the last class I told you that when you take any energy level, I mean energy band, there are many closely spaced energy levels within that. The distribution of electrons, this is one of the assumptions, distribution of electrons according to Pauli exclusion principle, it kept on occupying from the bottom. So any energy level if you consider, maximum occupation, maximum electrons allowed in any energy level is 2. That is one spin up and other one is spin down. So every energy level has the maximum capacity of 2 electrons, one with spin up and other one spin down. So now the electrons, all those electrons are start filling from the bottom at T equal to 0 Kelvin. So all of them are filled up to EF. So according to theory, this expression is valid, that for at any temperature, I mean at temperature T is equal to 0 K, for all those energy values, I mean energy states below Fermi energy are filled. That's what the meaning. So now coming to the second case, that is you are looking at the energy probabilities associated with the electron occupation of the electrons in the states above EF, above Fermi energy, therefore, if you the condition is that is the condition is again it is T equal to 0 Kelvin, and we are looking at the energy is the occupation of the electron or the particle above the Fermi energy. E minus EF, if you look at the value for E minus EF, since E is greater than EF, therefore the bracket becomes a positive quantity divided by K into T. Since T is 0, you have a something divided by 0, therefore it is infinity. So f of E becomes 1 by e to the infinity plus 1. If you add e, the value of E infinity is infinity, if you add 1 to the infinity, again it becomes infinity, therefore it is 1 by infinity. So 1 divided by 1, 0 goes up, Therefore, f of E becomes 0. Theoretically, it means that the occupation 0, it means there are no electrons or particles that have been present, that have been occupied at t equal to 0 condition for all those energy values greater than EF. That's what the meaning. It means f of E is equal to 0 implies that you don't have a particle sitting in the states above EF. So all those levels are empty. That's what the meaning. You don't have a probability. You don't see any particle that is being occupied the energy state above EF. It's not possible at t equal to 0 k. That is the meaning. So now it is clearly, this formula f of E clearly states that for all those energy values less than EF, that is for all those energy values they are below to Fermi energy are occupied, and for all those states above the Fermi energy are unoccupied at 0 Kelvin. So you have only probabilities, two probabilities, that all the energy levels below Fermi energy are occupied, are filled, and all the energy levels above Fermi energy are unoccupied. They are unfilled, they are empty at 0 Kelvin. So and we have another with respect to t equal to 0 k. What is the other probability? That electron, that is the regular case. See, we cannot always think of t is equal to 0 k. For any practical purposes, to understand the material, the temperature is always greater than 0 k. Okay. At any ordinary temperature, T is definitely greater than 0 k. It means we are thinking a practical situation where temperature is greater than 0 k. So now again look at the diagram, the similar diagram, that is f of E versus E, and you have seen that the property of occupation for all those energy values less than EF is 1, isn't it? And we are, for all those values for all those energy states above EF are 0. And we have chosen a situation right now t is greater than 0 k. Okay, so look at the diagram, second diagram at the bottom. That's what I was kept on explaining. And the topmost filled level is the EF here, and the dots they have been distributed. They are the positions of electrons with one spin up and other one spin down, up and down. And this is situation at t equal to 0 k. So now now we are right now trying to explain we're trying to understand the probabilities of occupation for the temperatures t greater than 0. Okay, if that is the case, the electrons they are close nearer to EF, the topmost levels, the close nearer to EF. Now they absorb energy and gets into the unoccupied states above EF. So it creates a valency or vacancies at the nearer to EF Fermi energy, and some occupations you will see above EF in the vacant sites. That is what takes place as temperature is increased. Therefore, if you consider, you look at the bottommost levels, E very much less than EF. See, if you take the bottommost electron to jump into vacant states, it requires very large amount of energy. Therefore, the electrons sitting at the bottommost energy levels won't take part in jumping into vacant sites. It is only those electrons they are much nearer to the EF, that is around near to EF, nearer to Fermi energy. They will absorb energy and gets into the vacant sites. So now for all those energy states that is very much less than EF, that it means bottommost almost bottom energy levels, they don't take part. Therefore, their property of occupation remains 1, because the electrons sitting at the bottommost energy levels, they will not jump into the vacant sites, they will remain there even the temperature is greater than 0. Therefore, the probability is still remains 1. But as you go up and up towards EF, you may expect some probability of electron jumping into the the vacant sites. If you choose an electron that is exactly sitting at EF, so then according to the equation E is equal to EF, therefore E minus EF becomes 0, therefore e to the power 0 is 1 plus 1, therefore f of E is equal to half. It means it tells you that if you are looking at the electron that is exactly in the that is remaining in the state EF, the Fermi level, that electron now picks up energy, thermal energy, and jumps into the vacant sites. So the probability of such an electron sitting in the Fermi level having Fermi energy is 50%. So the probability is 0.5. And if you go still, if you consider the energy level above EF, E greater than EF, certainly is you expect some electrons have been already started occupying because temperature is greater than 0. You may have a little probability, but as you go up and up, the value of probability is falls to 0. It starts rapidly goes to smaller value. Therefore, the curve here in the above first one, it gets a curve, the bend tail as temperature is increased. So now you see that at t equal to t greater than 0 k, I told you already that the electrons they are much nearer to EF will take part in getting into the vacant sites. Only a small percentage of electrons near to EF will move into the empty states. We'll understand this better in the one more diagram. Look at the diagram here. So the whatever I said so far is in the diagram right now. See the red dots, they represent the electrons. See in the first diagram t equal to 0 k, the red dots, they imagine they are the electrons. See the position, it's the electron. I told you that electrons. And now as the temperature is increased, use the second diagram t greater than 0 k, you see that electrons are moving into the above empty states. As the temperature is further increased, you expect more electrons jumping into the empty state. That's how it is. Therefore at t equal to 0 k, at E is equal to F, the probability of finding the probability of occupation for all those states E less than EF is 1 because you have the electron there. And above EF, you don't have the electron or the particle, therefore probability of occupation is 0. As temperatures increase, second and third, the last you see that. So as temperatures increase, you expect the electrons jumping into the vacant sites, starts entering into the vacant site. That will increase as the temperature is increased. So only those electrons they are nearer to EF here are taking part. Look at the diagram. Only the electrons very close to the EF, they are taking part in the conduction, and you don't see the electrons there at the bottommost, the lower ones. They don't take part in conduction, so they remain there. Therefore, even temperature is increased, T is greater than 0 K, the probability of occupation of the electrons for those E very much less than EF will remain 1. As temperature is increased, as you go nearer to the EF, those electrons will take part in conduction, they will move. So therefore f of E is decreasing. Initially it was 1, now it is decreases, and as per the equation, when it comes to EF, the probability of occupation becomes 50%, and as you still go further into the levels E greater than EF, the value of probabilities suddenly drops to towards 0. That's how what the explanation. So now we have seen that already with those formulae in the f of E, that is f of E is 1 for t equal to 0 k, and the energy for those energy states E less than EF, and you also see that f of E is 0 for all those energy levels above EF. You know that for t equal to 0 k. For those temperature greater than 0 k in the practical under practical situation, at T is equal to EF, you have the value 0.5 f of E, the probability of occupation is 0.5. Now you see that this f of E, the f of E is scattered between 0 to 1. What is the average value of 0 and 1? It is 0.5. So the average value of f of E is 0.5, where the energy is equal to E is equal to EF. What is that EF? EF is nothing but the Fermi energy. So now we can define Fermi energy as it is the most probable value or the average value of energy of those electrons which undergo transitions across the Fermi level at temperatures above T is equal to 0 K. So now what is the expression for Fermi energy at 0 Kelvin? This is the expression, that is EF is equal to h square by 8m within the brackets 3n by pi to the power 2 by 3. So this is the expression for Fermi energy at 0 K. See here in this expression you got h, Planck's constant, m is the mass of the electron, pi is a constant, n is the number of free charge carriers. So then a Fermi energy, value of Fermi energy EF is this. See, after you substituting the constant values for h, m, pi, etc., you got EF is equal to 5.85 into 10 to the power of minus 38 multiplied by n to the power of 2 by 3, where n is nothing but the number of free charge carriers available in that particular material. Okay. So if you take copper as a substance, then the value of n is 8.45 into 10 to the power 28 atoms per meter cube. So this value of n varies from material to material. So the Fermi energy, if you want to express in electron volts, this way the value is 5.85 into 10 to the minus 38 multiplied by this charge concentration. You will get the Fermi energy in electron volts. Otherwise, you know that it is in terms of joules. So Fermi energy of copper, from this expression you will see that it is 7 eV, 7 electron volt. We had a two situation, that is T is equal to 0 and T is greater than 0 K. So I told you that if you get an expression, if you try to get an expression for Fermi energy at T greater than 0 Kelvin, you will get this expression EF is equal to EF naught, where EF naught is the Fermi energy at 0 Kelvin. EF is a Fermi energy at T greater than 0 K. This EF 0, F naught refers to the Fermi energy at 0 Kelvin, and within the brackets, square brackets, 1 minus pi square by 12 into kT by EF naught whole square. So this is the expression. So now if you substitute again the constant values of pi, k, this EF naught, all those things, this the second term in the bracket happens to be a very small quantity compared to the first term. So this is the expression at T equal to T greater than 0 K. So now since second term in the bracket happens to very small value, we can approximate the Fermi energy EF is equal to EF naught. Therefore, we can assume whatever it is calculated the Fermi energy at 0 Kelvin, it was 7 eV, it also is valid at the temperatures greater than 0 K. Or you can say that the Fermi energy at room temperature, even at room temperature, is almost equal to 7 eV, because therefore it doesn't matter right now if you say that Fermi energy at 0 K is also 7, and yet the greater than T greater than 0 K is also nearer to 7. So it doesn't matter.